Okay, good morning. Hi, everybody. Can you hear me?
Yes, Prof. Good morning, Prof.
Right. Okay. So we continue our lecture from last 2 days. So I hope you fill up already the empty spaces here. Okay, using the formula. Okay. So in this case, k is equal to 1, k equals to 2, 3, and 4, including the error part. Okay. So the other examples where the process model is given by yk b1 z minus 1 over 1 plus a1 z minus 1 uk. Y is the output, u is the input, and this is the first order model. Okay, so the input output data is shown here. So if the k equal to 1, 2, 3, and 4 data, this is the input and this is the output. Estimate the parameters of A1 and B1. Okay, so B1 at the numerator and A1 at the denominator. Okay, so rewriting the model in the form of this equation, y is equal to k plus 1 minus A1 yk plus B1 uk. Or in the matrix form, we can simplify it as y is equal to psi beta. Okay, so therefore, from the given data, okay, we can form the matrices. So in this case, we carefully look at the y data and then put negative. Okay, so yk. So in this case, yk is minus 4, positive 4, minus positive 5, minus 5, so 0 is 0. So therefore, we can insert the value at the yk plus 1, which is over here. Okay, this one, minus positive 5 minus 5. 0 is 0, minus 2 is positive 2. So we get 5, 0, minus 2 for the yk. And for the uk is plus, okay, plus B1 UK, okay, UK. So this one should be 1 minus 1, 1. Okay, 1 minus 1, 1. Then we perform the matrices, which is here. Okay, Y, psi, okay. And beta, okay. So find the transpose of the psi. So this is 3 multiplied by 2 size, and this is 2 plus 3 because we interchange between rows and column. Okay. Due to transpose. Okay, and then the beta estimation is psi transpose psi inverse psi transpose. So multiply the psi transpose and psi. So this is the multiplication of psi transpose. So psi transpose is 2 multiplied by 3. Okay, multiplied by psi, 3 multiplied by 2. So you will get 2 by 2 matrices. Okay, which is this one. And then find the inverse, okay, manually. So how you find the inverse manually? From this particular subjects. So this one is how you find the inverse. So 3, 41, positive 1, positive 1. Okay. 41 minus 3 minus
ada determinant.
yeah, determinant, okay, minus 1 and minus 1, okay, determinant. So you get this one, right? Then psi transpose psi is 27, and then you multiply. So we'll get A1 0.55 and B1 is 2.5. So from the model itself, so we can enter as YK is equal to B1 Z minus 1 okay. So enter 2.5 Z minus 1 plus 0.55 Z minus 1 UK. Okay. So actually parameter estimation is you try to find the parameters value, the coefficients, okay? The parameter is the coefficients, okay? Coefficients of the transfer function of the model, okay? So using the formula again, this one, okay? So you substitute the K value. So K equal to 1, 1 plus 1, so estimation Y2, okay? So you will get 4.7. K equal to 3 minus 0.25. K equal to 2 and K equal to 3. Y estimation 4 is minus 2.5, which is over here, okay? So the error is between this one error is equal to the real value minus the estimation value. Okay, so in this case, 5 minus 4.7, 0.3, 0 minus 0.25, 0.25 minus 2 minus 2.5, 0.5. Then you find the MSE, minimal square error. Okay, so you get 0.134. So what is the formula of MSE? I can't remember. Okay, you can Google in the find in the Google the formula. Okay, I can't remember the formula. So you will get 0.134. This one is DIY. Okay, so I hope you can do it for yourself, and then share with me via WhatsApp. Okay, your answer via WhatsApp. Okay, using the simple least square, and then find this one as well. Okay. This table, okay, and do this table as well, okay. K, YK, UK, Y estimate K, EK, and MSE. Okay, construct the table. Analysis table. Okay, you do it on the piece of paper and then you cam scanner and send to me. Okay, so the answer is this one, right? Using the same questions, okay, but different data. Right, so overview from what we see of the least square, the simple least square. This technique actually works great, okay, but when come to the non-linearities, quantizations and noise, so it's a little bit breakdown and have a drawbacks, okay, have a drawbacks, and then we need to overcome these issues of non-linearities, quantization, and noise in the least square estimator, okay, the basic one. So how do we recover the good fitting? Is by improving the identification under noise and quantizations using a filtered least square. And this method, filtered least square, has the averaging for time domain, frequency domain, and lots of data will help to do the averaging much better, okay, to overcome all the issue above. So the filtered least square is shown here, where you have the input signal, or we call it as the excitation signals, and then connect to the digital to analog, and then go to the plant. Okay, so this one is actual, the real one, actual, and then it goes to the analog to digital converter, and then we'll goes to the filter input output using the same filter, and this is the filtered least square identifier algorithm to estimate the parameters or the coefficients of the model that we get. Okay, then therefore we get a model which is better than simple least square. Simple least square. Okay? Then the other one is filtered least square. Okay, so filtered is improve the simple least square. So how the filtered least square, the theory begin from the input output, where you find the transfer function, okay, estimation transfer functions, y over u, all right? And then from there, you construct the vector, the column for the data, and from there we start to calculate the filter, okay, using an iterative algorithm. Perform least square identification first, use the obtained denominator and 1 for numerator, filter the input and output, perform least square identification on the filtered data, use the obtained denominator and 1 for numerator, and repeat 3 until 5 until convergence. So when we do repeating for this convergence, computer actually helps a lot. Okay, computer can do it for convergence. So consider a model which is given here, y is equal to b divided by au, c divided by d. Okay, this one is it zeta? No, it's not zeta. What is the name of this? We can call it as okay, now we call it as a zeta. Actually, is a stochastic part. Okay, this is a stochastic part, input part, and the output part. Okay, so we postulate the filter f z minus 1 and multiply both sides by the filter, so we get these equations. So this equation now becomes a fy equal to b fu plus zeta, the stochastic part. So we think of fy and fu as a filtered inputs and outputs, okay, where this equation will come. Then we generalize the algorithms from zeta and y using a data, yk and uk, compute the simple least square estimates, which is this one, okay, beta estimate, analyze the residuals, and then fit to the auto-regressive model to model the ek, which give you this one. Then you filter the input and output and form the least square again and do again the computations. Okay, it's follow the simple least square, but we have to introduce a filter between both input and output. Okay, and then we repeat until it becomes convergence. Okay, so we consider a simpler case like this. Okay, y is equal to b divided by a u zeta. Okay, so using the GLS, generalized least square filter, both sides, so you will get this equation number 1. And from there, system, we follow the examples here, okay, where you are given xk and yk. uk and yk are the input output measurements. And zeta k is a zero mean discrete white noise sequence. Using the data given below, you find the simple least square and estimate one step of a generalized least square procedure where the filter value is given at k equal to 0. Okay, so this one is given. Okay, so the true parameters is 0.5 and 8 for A and B respectively. Okay, so this is the data given. Okay, for data from k equal to 1 until k equal to 4. So using a simple least square, because we need to do simple least square because we need the value that will be insert inside the filtered least square. Okay, so the system model is in the form of this y k plus 1 minus a y k plus b u k plus the stochastic part. Okay, so in the matrix form, we can write as y is equal to psi beta plus e. And this is the data given. So we construct data y. Okay, y is k plus 1. So k plus 1 is, if k is equal to 1, so y2. So y2 is 0, 9, and 3. So we insert as a column vector for y. Okay, column vector for y. Then we go for the psi. So psi consists of minus yk and plus uk. So first column is minus yk. So for minus yk, minus 16, 16. Minus 0, 0. Minus positive 9, minus 9. 16, 0, minus 9 go to the first column of psi. Okay. And the second column is the plus uk. Okay, so the input. Plus uk is minus 1. Positive minus 1, minus 1. Positive, positive 1, 1. Positive, positive 1, 1. So it will goes to the minus 1, 1, 1, second column. Right? So beta is under investigation, the unknown parameter, the unknown coefficient values. Okay. Then we apply the least square estimator, simple least square, which is this one. Okay. So you have to remember this formula. Okay. Estimated beta is inverse psi transpose psi multiplied by psi transpose multiplied by y. Okay. And then psi transpose psi is this one, using a calculator or using a computer or using a manual. Then inverse, and then psi transpose psi. So you multiply, so you get 0.56, 8.72. Okay. So we define the filtering. Okay, generalized least square, which is YF. So now you have to put F. F stands for filter. Okay. So YF is equal to YK over 1 plus A Z minus 1. UF is UK 1 plus A Z minus 1. So we use the value of A. The value of A here is 0.56. Okay. This value comes from the simple least square. Okay. Is the least square estimate of the parameter A. So substituting the equation, give a generalized least square for this problem as follows. Okay. So this equation now become minus AFYK plus UFK plus the stochastic part. So if A estimate is equal to A, the simple least square will be unbiased. So using equation 1, okay, using equation 1, compute the filtered input-output sequence using the filters. So we start with this one, okay? Minus A YFK minus 1 YK. So since K equal to 0 is given, 29.97. So use the value minus 16 from the table, minus 0.56 from the A estimate from the simple least square multiplied with the YF0, 29.97. You get minus 32.78. And this value will go to the second equation. The second equation answer will go to the third equation. The third answer will go to the fourth equation. Okay, so this is for YF1 until YF4. So we get this value. And this value will be constructed in the table, in the new table after we calculate for the U. So U is minus AUF K minus 1 plus UK. UF0 is given by minus 1.87. Okay, so we use the formula, which is a minus A minus UF, which is minus 1 from the data, minus 0.56 from the simple least square, and minus 1.87 from the given filtered value, okay, which is UF0, 0.059. So 0.059 will be used in the second equation. Second answer will go to the third equation. The third answer will go to the fourth equation. So this value will be constructed in the table as follows. Okay, so yeah. So UK, YK, UF filter, and YF filter. So you can see that 0.049 from the first one, second, third, and fourth. Okay, goes here. And then this one will go there as well. Okay, so now you have a new table, filtered, okay, filtered data. And then from the filtered data, you construct the YF, okay, which is the first part, which is this one, minus 18.36, minus 1279, and 3.716. But under filtering. Then theta filtering is minus UK, minus YK, minus YK, and positive U of K, but filtered. Okay, but filtered. So in this case, you take minus 32. Okay, minus 32, which is 32.78, minus 18.56, and then minus 1.279. So first column. And then for the second column is UK directly, which is 0.049, 0.972, and 0.45. Then you continue as a simple least square again, but under filtering. Okay, same thing, inverse. Then theta filtering transpose YF, then multiplied all, so you will get 0.54 and 8.55, which is an improvement from the simple least square estimates. Okay, so this one is filtering. The non-filtering one is this one, 0.56 and 8.72. Okay, so much better result in the simple in the filtering least square. So the examples, the next example is for the filtering as well. Okay, so using a data sequence below, estimate the simple least square, and then estimate the filtering least square. Okay, and YF0 is given here. So I give you the answer, but there is no solutions. So kindly again, you do it by yourself and then share with me your answer. Once you get your answer, cam scanner, and then WhatsApp directly to me. Can you do that?
Yes, Prof. When is the due date?
It's open. It's open.
Okay.
It's just give you some exercise during weekend. Okay. You can do it anytime once you are completed. So you just direct WhatsApp to me. Okay.
Okay.
Right. So next week we will go for the case study, chapter 5. Okay, so I hope everybody will try to do it and share with me the answer. 5 students, one student is in the immigration during his visa. Junyi, are you here? Junyi?
Yes,
Junyi,
Prof.
you are in Malaysia.
Yeah.
Kong Fan also in Malaysia. Nevin, are you in Malaysia?
Yes, Prof.
So one Chinese student, Wang Ji, in China, on the way back to Malaysia, and Hassan Abrar is not come, is in Bangladesh. So we will continue online lecture and test 2 online, but final exam will be face-to-face. Okay.
Okay.
Okay. So for the meanwhile, you can do the exercise and then do some assignments. Okay. For your assessment. So thank you very much, and I see you again next week. Bye.
Thank you, Prof.